Okay, welcome to Force Revision Part 2. I'm sorry I had to do that, but I was just interrupted at the front door, so my apologies. Okay, so where were we? We're working out the acceleration of this system here, and we've just decided that there's no friction and there's no other forces acting in this direction, which is the direction that the objects would be accelerating in this plane, and so we're pretty safe in assuming the only force acting to accelerate these objects is the 14 newtons. So that is the net force. So the net force is going to equal 14, and the mass, because all of this, is going to be 7. So 14 divided by 7 is 2. So the actual answer is 2 meters per second squared. That's the acceleration of both trolleys. Part B, what is the tension force in the string that connects the trolleys? Okay, well, that's an interesting question. That's probably something we haven't really gone into a lot of detail about. So let's have a close look at that now. The tension is the force in this string. Now, what's interesting about tension is that this is a really good example of Newton's third law. Now, let me show you why. This trolley, the 4 kilogram trolley, is pulling the 3 kilogram trolley, and it's pulling it in this direction. So there's a force there, which is the force of the 4 kilogram trolley trying to pull the 3 kilogram trolley. But Newton's third law, and this is an example of Newton's third law, if two objects are interacting with each other, the force of object A on object B is equal to the negative of the force of object B back on object A. In other words, if the 4 kilogram trolley is pulling the 3 kilogram trolley with a force in that direction, and we'll call that force the tension force, then that means, according to Newton's third law, which is this here, and this is where it's powerful, Newton's third law, that means that the 3 kilogram trolley must be pulling back on the 4 kilogram trolley with an equal and opposite force. And this is why, when you're actually towing something, you feel like you're being pulled back, you feel like you're being retarded or restricted, because the thing you're trying to pull along is pulling back at you in the opposite direction. So those two forces are equal and opposite. They are examples of Newton's third law. Remember, we said the normal force is not, but here is an example of Newton's third law in action. So how can we use that to work out the tension force? Well, what we need to do is simply have a look at one part of our system. Let's isolate one part of our system. So what I'm going to do, I'm going to isolate this part. So we're just going to look at that part there, okay? So let's have a look at this part of the system. Now, what do we know about it? We know that because this trolley is connected to this trolley, and we knew that this is all accelerating at 2 meters per second, we know that this must be accelerating at 2 meters per second squared. Sorry, 2 meters per second squared, not 2 meters per second. So we know the acceleration on this trolley is 2 meters per second squared. And we know that the only force that can accelerate this trolley that's acting on this trolley is the force through this rope, which is the tension force. So the tension force is what's doing the accelerating on this trolley. We also know the mass of this trolley. So by isolating one part of the problem, we can now work out what the tension force is, because here the tension force in this part of the problem is the net force acting on the 3 kilogram trolley. And so let's work it out. So we know that the net force, using Newton's second law, the net force, and this was part B. Part B. So the net force is equal to MA, which is going to equal 3 kilograms multiplied by the acceleration, which is 2, and that equals 6 newtons. So that tells us that the tension force here is 6 newtons. But hang on, then if that's 6 newtons, then this has got to be 6 newtons. So, anyway, we've answered question B. I have a feeling I know what question C is going to be. What is the net force on the 4 kilogram trolley? Okay, we'll check this out. Here's our 4 kilogram trolley. Now, there's 14 newtons pulling on it this way, but guess what? There's 6 newtons acting back on it this direction due to our Newton's third law. So the net force acting on our 4 kilogram mass is going to be 14 newtons, take away 6 newtons. And that equals 8 newtons. So the net force acting on this trolley, oops, I'll go for another colour, I think. Net force acting on this trolley is equal to 8 newtons. Now watch this. Check this out as a beautiful confirmation how everything just works lovely, in a lovely manner. Here's the net force. This is the net force acting on the 4 kilogram trolley. Let's work out acceleration. The acceleration will equal the net force on the trolley divided by the mass. So if we're just talking about the 4 kilogram trolley, the net force is 8, the mass is 4, equals 2 meters per second squared, which is, of course, what the original acceleration was in the first place. So it all works out absolutely beautifully. But let me just reiterate, when dealing with a problem where there's two objects connected by a cable or some sort of a rope, one thing to remember is that the tension on this cable, whatever is what is an example of Newton's third law, and whatever force is acting in this direction must be the same as the force acting in the opposite direction. And then once you know that, you can isolate one part of the system and work it out. I could have actually done this problem by isolating this part and knowing that the tension force was 6 newtons and the force this way is 14. As I just did a moment ago, I could work out that the net force there is 8 newtons and therefore the acceleration is 2 meters per second squared. So it doesn't matter which part you isolate, but in general you want to isolate the one where there are the least number of unknowns. In this particular case, in both problems in both parts there's only one unknown, which was the value of t. So that's question 6, I think, all of it. No, one more. What would be the acceleration of the 4 kilogram trolley if the string between the trolleys was cut? Okay. Well, if we cut the trolley, if we cut this string here, then what we're effectively doing, we are in fact getting rid of all of that. So that means now this is just a basic Newtonian problem like the ones we would have done earlier. So we've got a 4 kilogram mass. So we'll just draw a new picture if you like. A 4 kilogram, and I might change my colour. We've got a 4 kilogram mass. There's a force of 14 newtons pulling it along. What's the acceleration? Well, it's the net force over the mass, which is 14 newtons divided by 4, which is going to be 3.5. So it's 3.5 meters per second squared. So there you go. That's question 6. Question 7. Okay, clear that. Question 7. The cable holding a lift would break if the tension in it were to exceed 25,000 newtons. Okay, so let's draw this step by step. So it's question. This is quite a challenging problem. Let's see how we go. So we've got an elevator or a lift, and there's a cable. Obviously, it runs on a cable. Now, that's our cable, and that means it'll break at 25,000 newtons. So if it has to apply, if a greater force than 25,000 newtons is applied through that cable, it will snap. So what that's really telling us is the cable, the maximum force that cable can exert is 25,000 newtons. And the cable is, of course, going to be pulling the elevator up. Okay? Now, so if the 480 kilogram lift has a load limit of 24 passengers, what is the maximum possible upward acceleration of the lift without breaking the cable? That's interesting. What an interesting problem. So the lift itself has a mass of 480 kilograms. So the lift has a mass of 480 kilograms, and it has a maximum capacity of 24 passengers, each of 70 kilograms. So if we could imagine, it's a big lift, by the way. So there's 24 people in here, a maximum of 24 people. I won't draw all 24, but you get the idea. And each of those people is 70 kilograms. So that means that the maximum payload is 1,680 kilograms. In other words, the payload, which is what is being carried in the elevator, it's 24 people multiplied by 70 by 70, and that's 1,000. So that's 1,680 kilograms. So the payload is that amount, and the lift itself weighs this much. So the total mass of the lift plus the payload, which is really what the cable's got to try to accelerate, the total mass is going to be both of those added together. So total mass equals 1680 plus 480. And that equals 2,160. 2,160 kilograms. Okay. Now, think about this. If we're going to accelerate this lift and everyone in it in that direction, the greater the acceleration, the greater the net force necessary to create that acceleration. So there's going to be, if we're told that the greatest amount of force we can exert is 25,000 newtons, we can't go over that figure. That means there's a certain acceleration we can't go over. And so let's work that out. So that the acceleration that goes with this maximum force trying to lift this total mass is going to be the following. It's Newton's second law again. It's going to be the net force acting on all of this divided by the mass. Now, the question is, what's the net force? Is that the net force? No, it's not. That is the cable force. That's the force pulling it up. Okay? You might think of it as the thrust force. The thrust cable force. It's not the net force. So we need to identify what the net force is in this problem before we can solve it. So in order to do that, we need to identify all the forces acting. So I'm going to draw another diagram, And we'll just get our data on the right hand side here. So we know that the total mass is 2160 kilograms, and we know that the maximum thrust force, or the maximum cable force, equals 25,000 newtons. Okay. So, let's now, and the lift itself was 480 kilograms. Okay. So, what I'm going to do is clear that part off and clear that part off and that as well. And now let's redraw the problem with all the forces acting. So what we've done so far, we've got a visualization of the problem. So let's now try to solve it. So there's our lift. And cable force. Nope. So it doesn't matter. Okay, so that's going to be 25,000 newtons. But we also know there's a weight force acting here. Now the weight force is going to be the weight of the payload and the weight caused by the lift itself. So it's going to be pretty massive weight, or pretty large weight force, and let's draw that in. So, I'll go with blue, I think. So there's another force acting down, which is the weight, the total weight force, which is going to equal mg. Now going with g equals 9.8 because the rest of the problems are consistent with that. So it's going to be the total mass of our whole object here, which is 2160. There's the mass of our elevator multiplied by 9.8. So that equals 21,168. 21,168 newtons. So, if we've got a weight force, a pulling force on the cable of 25,000 and a weight force of 21,168, as a matter of fact, this probably should be a little bit shorter than that, shouldn't it? So, what are we doing? That. Therefore, the net force in this problem, the net force acting on our elevator, will be the cable force. I'll call that the thrust force. Cable is just acting as a thrust in this particular problem. It's actually trying to drive the elevator upwards. So the net force is going to be the thrust force plus the weight force. All the forces add together make up the net force, okay? Now, let's assign our directions. So we'll call up positive, because the elevator is moving in upward direction, I'll call up positive and down is negative. So the net force is going to equal our positive thrust force, which is 25,000 newtons, then plus our weight force, which is a negative force because it's down, 21,168, so it's going to be minus 21,168. And that equals 3,832. 3,832 newtons. That's our net force. So, if that's the net force, then the acceleration will be the net force over the mass which is going to equal 3832 divided by 2160, and that equals 1.77. That's 1.77 meters per second squared. So that is telling us that, that's the maximum acceleration, given that this is the limit, the upper limit of the force that can be applied through the cable. Obviously, a stronger cable, we could apply more thrust. This force could be bigger, therefore the net force could be bigger. Therefore, we could accelerate more. Okay, so there we go. Now, question 8. We've got a couple of diagrams. This time, you have to work out. They've provided the net force. You have to work out what is the missing force. So in the diagrams below, the net force is shown in red, along with all but one of the contributing forces. So one of them has been left off. Determine the magnitude and direction of the missing force in each of these situations. So there's 2 situations there. Okay, let's have a look at it. So clear, and it's question 8. So this one we've got 400 and 200. So I've got a 400 Newton force. Try it again. A 400 Newton force acting that way. (200 Newton acting that way. So it's 200. This is 400. And we know the angle is 60 degrees. So and we know that the net force in this particular problem is 0. So there's some other force acting here. There's some other force acting here which will mean that when we add up all 3 forces, they add up to 0. The trick then is to work out, well, what do these 2 forces add up to? And they'll add up to some force in some direction. So clearly then, the force that will cancel those out is the force that's the same length, but in the opposite direction. So let's add these 2 up. Now you notice that they're acting at sort of weird directions or to each other. So what we want to do is work out the components. So what I'm going to do is look at my 400 Newton force. I'm going to work out its vertical component. Actually, I think we've got a compass rose there. Come to think of it, yes, north, south, east and west. So I'm going to work out its southerly component and its westerly component. So that's what we're going to do. And, oh, it's a nice green. Okay, so there's our southerly component, and there's our westerly component. So there's the southern component, from there to there, and here's our westerly component. So I'm going to replace this 400 Newton force with a southern component and a western component. So let's work out this component first. This is going to be the cos of 60 times 400, and that's just another trigonometric problem, of course. So it'll be 400 times the cos of 60, and the cos of 60, if you know your maths, is the same as the sine of 30, which is 0.5. So that will equal 400 multiplied by 0.5, which is 200. So that's 200 newtons. Okay, so that's 200 newtons there. Now, this one here will be 400 times the sine of 60. And the sine at 60 is 0.866. It'll be 400 times 0.866. And that will equal 346. 346.4 newtons. Okay, so what we can now do, and I'll do this in a fair bit of detail because it's important to be able to understand components and what they really represent. So now we can now redraw our problem showing the actual components. So we've got a 200 Newton force acting that direction. I've got a 200 Newton force acting down in that direction. Actually, I'll just draw those in first. So there's that's 200 down. That's 200 up. Now, I also know that there is a component acting this way, which is 346.4. Now I could draw it there, I could draw it there, it doesn't matter, but I'm going to draw it up here where they all meet. So another force acting that direction, which is a little bit longer actually, it's 346.4. 346.4. So, that force there is this force here, that one there is that one there, and that one there is that one there. So you can clearly see, I hope, that that and that cancel. So that just leaves this force, which is unbalanced. So if we want the net force to be zero, then we've got to come up with a force that is equal and opposite to it. And that's probably pretty clear what that is. It'll be a force of 346.4 acting in that direction. So the missing force was 346.4 acting in the east direction. That's the missing force. And it's the missing force so that now if you add that in, all these four forces will add up to zero. Right, the second problem, we've got three 200 Newton forces and these two are acting at 30 degrees to the easterly direction and the net force is 200. So let's see what's going on there. Okay, so we've got a 200 Newton force and we've got 200 Newton force that way and a 200 Newton force that way, 200, 200, 200 newtons. We know that these forces here are 30 and 30. Sorry, angles, beg your pardon. Those angles are 30 degrees. But we also know, because we're told in the problem, that the net force in this situation is actually 200 newtons in that direction, which is east. So we've got to work out what is the missing force that will give us a net force of 200 newtons in the east direction. So there's one more force we've got to put in here to work out, to make this add up to 200 newtons in that direction. So the way we do this is just like we did in the previous example, which is to firstly work out what these three forces would add up to, and then add the missing force so that we end up with a net force of 200 to the right. So let's do that. Okay, so once again, because we've got these different angles happening, we're going to break these two forces here, the two white ones, into components. So I'm going to So one of the components is that direction, and there's two of these forces, so there's going to be two components acting in that direction. There they are. There's two of them. And this is very similar to a problem we did earlier. And you might remember that these components here, that component there and that component there, which are acting in opposite directions, they will in fact cancel. So really all we've got to do is work out the green component, and there's one for this triangle and one for this triangle. So we just work out one of them and then double it, and that will give us both of the components. And let's see where we're at after that. So let's work out the top one, okay? This one here. So it's the adjacent side of the triangle. So it's going to be 200 multiplied by the cos of 30 degrees. And the cos of 30 degrees is 0.866. So it's going to be 200 times 0.866, which equals 173.2. 0.2 newtons. So that force on this triangle is 173.2, but guess what? There's a force there, which is also the same. So it's also 173.2 newtons. So that means in total, remember the two red forces have cancelled because they're the same size but in opposite directions. So what we're left with is an object. Try that again, I think. An object, there's an object there that all these forces are acting on, where we've got the two green forces adding together. So 173.2 plus another 173.2 in that direction. So what we've got is 173.2, 173.2 again, and then 200 off in that direction. So it's 200, 173.2 and 173.2. So our net force here is going to be, well, this is going to be 173.2 multiplied by 2 is 346. So these two together add up to, don't want that to be happening. Those two together add up to 346.4, and this part is 200. So the net force at the moment without our missing force is going to be, it's going to be 346.4 take away 200. And that will equal 146.4 newtons to the right or east. So our net force so far is 146.4 newtons to the right. That's all these forces take into account, but we want a net force of 200. So what do? Well, that's right. We add an extra force in to make all the forces add up to 200. So what we've actually got then, right now, if we add up all the forces, is a single force, and I'll draw it in blue. We've got a single force of 146.4 newtons. So all those forces here, all these forces here, are acting together as if they're producing a total force of 146.4 newtons. So the question is, what do we have to add? What do we have to add? What's that unknown amount that we have to add so that the total adds up to 200 newtons to the right? or east. And that's going to be 153.6. So that force there is going to equal 200 take away 146.4. In other words, to do it another way, using a force equation, we know the net force is going to equal 146.4 plus our unknown force, which is in the same direction. So if we'll say that direction's plus. Therefore, X will equal the net force minus 146.4, and the net force is 200. It'll be 200 minus 146.4, which will equal, what did I say? 53.6, I think. 146, so yeah, that sounds right. So that's the missing force. The missing force, this missing force here, we need another force in there, which is 53.6 newtons. That's the missing force. Okay, question 9. A skateboard of mass 56 kilograms is rolling freely down a straight incline. The motion of the skateboarder is described in the graph below. Righto, what have we got here? So we can see their speed's increasing at a constant rate. Look at that, a constant rate. This is a speed time graph. What do we know about the gradient of a speed time graph? The gradient of a speed time graph is the acceleration. The gradient is the acceleration. And that's a constant gradient. So the acceleration is constant. And if we actually worked out the gradient, that would probably give us the acceleration. So what is the magnitude of the net force on the skateboard? All right, so let's have a look at this problem. So this is question, sorry about that, question 9. Okay, so the gradient of a graph is simply its rise over its run. So it's got a rise, make sure our units are correct. We're in meters per second here, that's good, and we're in seconds here, so that's all fine. So the rise is 6 and the run is 8. So the acceleration in this problem is 6 over 8, which is 0.75 meters per second to the negative 2. Okay, so what is the magnitude? Then that's acceleration. So now we can work out the magnitude of the net force, because we know that the skateboard has a mass of 56 kilograms. Okay, now once again, remember the acceleration will directly give us the net force. They are directly tied together. Acceleration and net force are tied together using Newton's second law. So the net force will equal ma. That's Newton's second law, which is the mass of the object, which was the skateboard, which is 56 kilos, multiplied by the acceleration, which we've just worked out, which is 0.75. And that gives us a net force of 42 newtons. So we could work that problem out really without any diagrams, because we just know the connection between acceleration and net force. We didn't really need to know what was happening. But I imagine the next part of the problem we will. If the friction force resisting the motion of the skateboarder is a constant 140 newtons, at what angle is the slope inclined to the horizontal? And yes, I was right, we now need to draw a diagram of the situation. So, in other words, there's a friction force acting here. It's resisting the motion of the skateboarder. Now remember, the skateboarder is, from memory, rolling down the slope. is freely rolling down a straight incline. So they're rolling down the slope, and we know their acceleration because we've just worked it out. And we know there's a constant friction force of 140 newtons. You have to work out the angle. Okay. So let's summarise our information. We know that the net force, we just worked it out, equals 42 newtons. We know that the mass of the skater is 56 kilograms. We know that the friction force equals 140 newtons, and that acts against the direction of motion. Let's just check that, 140 newtons it was. And we have to work out the angle of the inclined plane. So what is the angle that the whole thing is sloping at? And remember that the acceleration, we know the acceleration is 0.75 meters per second, but I don't think we'll need that anymore. Okay, so let's clear off this working. Right, so let's now draw a picture. So we've got a ramp, and we don't know the angle in this problem. That's the issue. We don't know the angle. We don't know that angle. Now I'm just going to draw a blob to represent the skater. And here we go, there's my blob. It's a pretty blobby blob, but that's okay. So there it is there. There's my skater. And we know that they're rolling down the ramp. So let's mark in their velocity. So we know that they are moving with a velocity down the ramp. We don't know what the velocity is at this stage. Oh, we could probably work it out because we had a graph there, but that's not really important. What we have to work out is the angle. So let's draw in the forces now, and we'll draw them in blue. Okay, so we know there must be a weight force acting straight down. And that will equal mg. And we know the mass of the skater is 56, so it's going to be 56 multiplied by 9.8. And that will equal 496 newtons. Okay. We also know, of course, that there's going to be a normal force. Let's draw that in. That's going to be at right angles to the ramp, and I'll draw it in there. There's my normal force. We also know that there is a friction force. A friction force with 140 newtons. And friction always acts against the direction of motion. So if we know that they're rolling down the slope, then we know the friction must be acting against that direction. So friction must be acting this way. And we know the value of the friction is 140 newtons. Now, we also know that all these forces are producing a net force of 42 newtons down the slope. They're getting faster down the slope. So there's one more force, well, there's no more forces, but we need to be able to analyse these forces, break them down, and find out what component of our weight force is acting down the slope as well. So the next issue in this problem is to break down that weight force into two components. So we need to break it down, and we'll do it in green. We need to we'll do it in yellow. We need to break it down into a component which is at right angles to the slope, and write a component which is parallel to the slope. So there's another force. So let's have a look at the forces that are acting here. We've got a normal force, we've got the component of the weight acting down the ramp, and we've got a friction force. Now, I'll just fix something here. That friction force, have I got a rubber? Do I have a rubber? Yes, I do. The friction force is actually I should draw that shorter, because the net force is down the ramp. So this force is going to have to be bigger than the friction force. Okay. So let's just make sure I've got everything set up correctly before we proceed with this problem. So let's just check everything again. The mass of the skater is 56 kilograms. They're rolling freely down a straight incline. The motion of the skateboarder is described in the graph below. And so we see they're building up speed over a period of 8 seconds at a constant rate. So we know there's a constant acceleration. Question A is, what is the magnitude of the net force? Well, we did that. Question B, if the friction force resisting the skateboard is 140 newtons, what is the angle? Okay, so that's what we have to work out. What is this angle? So let's call this, we don't know this value here yet, but what we do know, it's going to be, I'll use white now, I think. I know that if that's theta there, the unknown angle, I know that that's theta there. And I know my weight force. I know that my weight force is 496. And because I know my weight force, I know that that component there is going to be the sine of the angle multiplied by the weight force. So that force there, the yellow force, is going to be the sine of theta multiplied by the weight force, which is 496. Oops. Sine of theta, not sine of 30. Okay. So it's going to be sine of theta. So I know that that's cancelled with that, because I know that the object is accelerating down the ramp, and therefore all of these perpendicular components must cancel. So the only forces that are acting in this direction, up and down the plane, are the friction force and this component of the weight force. So I know that the net force, which must be acting this way because that's the direction of the acceleration, so the net force, I'm going to call that direction positive, by the way, so that's positive, therefore that direction is negative. The net force is going to be 496 times the sine of theta. That's the weight component. That's the yellow part of the force. That's the yellow force there. That's this thing here. Okay? And plus the friction force. But the friction force is a negative force. And so it's going to be minus 140. So those two forces must come together, or add to, or subtract or add, to make for F net. Now we know that F net is 42 newtons. So we know that 42 equals 496 times the sine of theta minus 140. Okay, so what I'm going to do, we now need to work out what theta is. So I'm going to take this and move it to the other side of my equation by adding it. So 140 plus 42 is 182. So 182 is equal to 496 times the sine of theta. Now I'm going to divide both sides by 496 to get the sine theta on its own. So therefore, the sine of theta is going to equal 182 divided by 496. So 182 divided by 496 is actually 0.367. So the sine of theta equals 0.367. So what's theta? Well, theta is therefore the second function, or the inverse sine, that's the long way of writing it, second function sine of 0.367. There's a better way to write that. I'll go it up here because I'm running out of space. Theta is actually equal to the beg your pardon, arc sine. Arc sine is inverse sine, that's another way of writing it, of 0.367, or inverse sine if you like. So basically what it means is you type in the inverse sine button. So it's going to be 0.367 and inverse sine, and that gives us an angle of 21.5 degrees. So theta equals 21.5 degrees. And that is the angle of the ramp. Okay, nearly done. Righto, question 10. A person jumps out of an aeroplane with a parachute strapped to their back. The mass of the person and parachute is 90 kilograms. The value of K for the person with the parachute not deployed is 1.57. When the parachute is deployed, the value of K is 27. Determine the terminal velocity of the skydiver before they open their parachute. Okay, so question 10. So the person and the parachute is 90 kilograms. So it's question 10. We've got a person who's just jumped out of an aeroplane, and they've got the parachute strapped to their back. Having great fun. They're accelerating downwards, and their mass is 90 kilograms. Right, now the two values of K were 1.57 and 27. Yeah. So that's when the parachute's not deployed. And K equals 27 when the parachute is deployed. So, what's the question? Determine the terminal velocity of the skydiver before they open the parachute. Okay, so terminal velocity occurs, and we should know this quite well now. Terminal velocity occurs when the weight force, mg, is completely balanced by the drag force, when the two cancel each other out. So when terminal velocity is reached, my drag is exactly balanced with my weight force. Now drag is equal to kv squared. So if the two are equal and opposite, that means, and we just want to work out the value of v, so we don't need to worry about signage. So what we now know is that kv squared, when terminal velocity, at terminal velocity, kv squared equals mg. So therefore, v squared will equal mg over k. Therefore, v will equal the square root of mg over k. So that's our term, that's our v term, terminal velocity. So it will equal the square root of the mass, which is 90, times g, which is 9.8, divided by k. Now it's not deployed, so it's 1.57. So that will equal 90 times 9.8 is 882, so it'll be 882 divided by 1.57, and that equals 561.8. 561.8, and the square root of that is 23.7. So that's meters per second. So terminal velocity before the parachute is deployed is 23.7 meters per second. Times that by 3.6, and that will equal 85.3 meters per second. 85.3 meters per second. Seems a little bit low, actually. Let me just check something. So mass is 90. I think this is probably too high a value when not deployed. So kV squared equals mg. So v squared is mg over k. So it's going to be mass, which is 90, times g, which is 9.8, divided by k, 1.57, mg. That looks right. Yep. Yeah, so, yeah, okay, so a bit on the low side, but never mind. Okay, so part B, draw a series of diagrams showing the forces acting when the parachute is opened. What is the new terminal velocity? Okay. So, as the parachute's opened, let's do this as a couple of diagrams. So, let's say that diagram A, the parachute has just fully opened. Just fully open, but there's still they'll still moving very, very quickly, which means that our drag force suddenly the weight force hasn't changed, and so weight force will still be 882 newtons down, but suddenly K has gone from being It's gone from 1.54 or whatever, or 57. It's changed to 27. So it's gone from that value to that value, which means our drag force is going to absolutely explode. It's going to be huge. So our drag force is suddenly going to get really large. Now, our weight force hasn't changed, but our drag force has suddenly become huge. So our net force will in fact be in that direction. The net force will be up. But hang on, they were moving down. They're falling in that direction. So the net force is going to be up, which means the acceleration is going to be in that direction. So it's going to start slowing them down because the acceleration is acting against the direction of motion. So in the next diagram, we could then draw the fact that now they're going to slow down. So in the second diagram, there's our parachute and there's our person. Now in this particular diagram, and perhaps in the first one I should have drawn a longer velocity vector because they're traveling pretty quickly. In the second diagram, now they've been decelerating for a while, now they're much slower. So they're still moving downwards but at a much slower speed. Now because they're moving much slower, remember drag is equal to kv squared, which means if the velocity is reduced, the drag's going to be lower. So the drag's going to shrink. So drag would have come down. Okay? Maybe still not quite the value of the weight force yet, but so that might be the weight, which is still 882. Now the drag force might now just be a little bit bigger, which means that our net force will be just maybe a very small net force there. So maybe you're going to have a tiny bit more deceleration as they're still slowing down a little bit. So eventually they'll keep slowing down to reach this point. They'll reach the point where there's a parachute, there's the person. The weight force is 882 down, and the drag force will be, they would have slowed down to a point where the drag force is 882 in the upward direction. The two forces cancel each other out, therefore acceleration equals 0, and the new terminal velocity will be when mg equals kv squared again, but now k equals 27. So you could recalculate the value for the new terminal velocity, and it'll be the same as before. It'll be v equals the square root of mg over k, which is going to be 882, square root 882 over 27, which is 32.6, so it's going to be the square root of 32.6, going to be very slow, isn't it? So 5.71. So the new terminal velocity will be 5.71 meters per second. And that is it. So thanks. I hope this was helpful.